Hey, Andrew Wolf here. In this video I'm going to talk about peptic ulcer disease, but before I get into talking about the pathophysiology, I want to talk about the physiology of the stomach, in particular the physiology of acid production, the regulation of acid production, and the physiology of the protective mucosal surface of the stomach. Okay, so let's just review some of the mucosal layer of the stomach. So now, if you remember, the mucosal layer is very irregular in the stomach. It's filled with these sort of gastric pits, and I'm going to kind of draw one of these up close. So here we have a big gastric pit, and actually they're very, very deep if you look at the histology, and you can find pictures on in images, Google Images, very easily, that show you the histology of the stomach, and they're very, very deep pits. Now, on the surface here, we have a columnar epithelium, and the columnar epithelium is interspersed with what are called foveolar cells. And the foveolar cells are actually very similar to the goblet cells in the intestines, and their major role, as you might expect, since they are similar to goblet cells, is to produce mucus that lines the stomach. Now, this mucus, and I'm going to talk about this a little bit more, has a few major components. Obviously, it has water in it, but it also has a lot of mucin, as is typical of mucus. But then it has a special ingredient that's unique to the stomach, and that is gastric surfactant. Now, if you remember, a surfactant is a molecule with that's very similar to, actually it has a phospholipid component, so it has a hydrophobic end and a hydrophilic end. And this provides a thin, impenetrable barrier that lies on top of the mucus and protects the mucus, that protects the cells from any charged molecules. In particular, the charged molecule that we're really worried about here is hydrogen, the hydrogen ion. So this provides an impenetrable barrier protecting the mucosal cells. And again, those are called foveolar cells. And then, sort of moving down the neck into the gastric pit, we continue our columnar epithelium. And when we get sort of midway down, we have the parietal cells. And that I've seen them they kind of look like little cellular volcanoes. And these are parietal cells. Now, parietal cells pump out hydrogen ions. And I'm not going to get into the chemistry of just how they do that in this, but just be aware that their major role is to produce acid when stimulated, and we'll talk about how they're stimulated in a few minutes. Okay, so acid secretion. Okay, and one interesting cell here is called the ECL cell, and this ECL cell actually produces histamine. And it's actually stimulated by the parasympathetic nervous system, by acetylcholine from the parasympathetic nervous system, to release histamine, and then the histamine makes its way to the parietal cells to stimulate acid secretion. Now, 20 years ago or so, we thought that this was the major stimulus for acid secretion, and we invented a class of medications called histamine blockers. And it turned out that these work fairly well, but then we learned that that parietal cells are actually directly innervated by and respond to acetylcholine themselves. So that's why histamine blockers do reduce acid production, but they don't decrease it all the way. Now, if you give someone a PPI, on the other hand, a proton pump inhibitor, a proton pump is the mechanism by which the parietal cells produce their hydrogen ions and secrete acid. So if we give a proton pump inhibitor, it's a much more powerful drug at preventing acid secretion because it's not just dependent on one pathway. Now our columnar epithelium continues all the way down to the bottom, and then sort of at the bottom of the pit we will find what are called chief cells. And the chief cells secrete pepsinogen. And pepsinogen is an enzyme that breaks down protein, so it's a protease. And this is also stimulated directly by acetylcholine. Now, the mucosa varies from one part of the stomach to the other. We have, cardiac mucosa that is unique. And then we have the mucosa of the body of the stomach, and then we have mucosa in the antrum. Now, the antrum of the stomach actually has a, similar gross anatomy to it, but it has a different collection of cells. For one thing, it doesn't have a significant number of parietal cells. And for another thing, it has some other unique cells. It has some endocrine cells, and one is called the G cell and one is called the D cell. So the G cell, let me be consistent with my colors. The G cell is stimulated by the presence of amino acids. And G stands for gastrin. Gastrin is a hormone that goes into the bloodstream and travels around the bloodstream and then zeroes in on its target, which is the parietal cells, and stimulates acid secretion. So that's three things that the parietal cells respond to. Just to remind you, they secrete acid in response to acetylcholine from the parasympathetic nervous system, from gastrin, from the G cells, and from histamine from the ECL cells. Now, the other cell here in the antrum is called the delta cell, and the delta cell is stimulated by low pH or acid. And when there is low pH, the delta cell is stimulated to release somatostatin, and the somatostatin suppresses the parasympathetic nervous system. So it has a negative effect on the parietal cell production of hydrogen. So we have here, so these ones are histamine, gastrin, and the parasympathetic nervous system are all positive, but here we have a negative effect from somatostatin. So the regulation of acid production really sort of occurs in the antrum of the stomach because of the G cells that are stimulated by protein to produce gastrin, which stimulates the parietal cells, and the delta cells, which provide a negative feedback for high acid levels by producing somatostatin, which slows down the parasympathetic nervous system or suppresses the parasympathetic nervous system to decrease acid production. Okay, now I want to go on and talk about the protective mechanisms, and I've alluded to some of them here. So this is just going to be putting them in a different status. So what are the protective mechanisms of the mucosa? Well, first of all, why do we need a protective mechanism? Well, because we've got low pH, which is toxic to most cells, because we've got a pH of, sometimes as low as 1 to 2. And we also have pepsinogen, which is a protease that could also be directly toxic to cells. So the stomach needs to protect itself from its own secretions. So protective mechanisms are very critical. So the first protective mechanism that we have is regulation of acid production. And this is very important because if we don't have a pH of 1 to 2 all the time, it only gets very low at times when there is food in the stomach, in particular amino acids. So this regulation of acid production occurs because of the G cells and their secretion, which is gastrin, and the delta cells and their secretion, which is somatostatin. And this provides that negative feedback loop. So regulation of acid is very important. The next part is the mucosal barrier. Now, there are adaptations of the mucosal barrier that make it very unique in the stomach. First of all, we have unique adaptations to the columnar epithelial cells. And we don't know the exact mechanism of this, but we know that the apical surface, the surface that points into the stomach, is very resistant to a low pH. So the cell is adapted so that the apical surface cannot be damaged easily by low pH. However, this is not true for the lateral and basilar surfaces. So this mechanism works quite well if the epithelial cells remain intact. Apical membrane resistance. Okay, so you can imagine what would happen if usually there is a very tight border between the columnar epithelial cells, but if one of these cells dies, then the acid will have direct access to the lateral or possibly even the basilar surface, and that cell is going to be damaged. And next we have gastric surfactant, and I talked about that above, how that works. Prevents water or any charged or polar ions from getting through the layer of surfactant. Now, interestingly enough, we talked in my last video when we talked about alcoholic cirrhosis. One of the interesting things about alcohol is that it is a solvent for lipids and phospholipids. So if you drink a lot of alcohol, one of the things that it can do is dissolve or break through the layer of gastric surfactant. So alcohol can that's one of the ways that alcohol can start to disrupt this mucosal barrier and help to lead to mucosal injury in the stomach and cause gastritis. And then, of course, we have the mucin. So the mucosal barrier is made up of specially adapted epithelial cells with the apical membrane resistance, gastric surfactant, and mucin. Now, the third element, I think, is often underappreciated. The third element of protection is the remarkable ability of the gastric mucosa to repair itself. So epithelial repair. And people have actually done studies in rats where they have completely denuded the gastric mucosa of the entire top layer of the columnar epithelium. So the gastric mucosa was completely stripped of all epithelial cells. And they noticed that the epithelial cells actually migrated back to the surface and repaired themselves within 1 hour. So there is a remarkable ability to repair. And so what happens is you have some kind of acute injury. Usually it doesn't denude the entire mucosa, it probably will just denude part of it, but even if it denuded the entire mucosa, it has the potential to repair itself. What happens then is we have a hyperemic response. So we have vasodilation of arterioles and increased blood flow to the mucosa. And this is an important step in the next step, which is the formation of a mucoid cap. So you need this extra blood flow to produce the fluid to create a whole bunch of mucus. And this is not typical mucus, it's actually very, very thick mucus, and it makes a very thick protective layer. And then we have remigration. Migration of epithelial cells from deep in the gastric pits to the surface. Now I'm going to talk about how all of these things can be disrupted, and it's disruption of 1, 2, or 3 of these mechanisms that can lead to peptic ulcer disease. And typically, the causes of peptic ulcer disease impact all 3. Regulation of acid, disruption of the mucosal barrier, and disruption of the epithelial repair mechanism. So in this country, the major causes of peptic ulcer disease is H. pylori. And now H. pylori is an interesting infection. The epidemiologists suggest that about 50% of every person in the world is infected with H. pylori. However, fortunately, only about 50% of those have a virulent form of it that can actually cause significant disease. And then of that 50%, about 15% of those people will end up developing a peptic ulcer during their lifetime. So I believe that brings us to about 3 to 5% of people during their lifetime will have a peptic ulcer. Well, what does H. pylori do? It's a nasty little organism that is perfectly adapted to live in and feed in our stomach. So it does 2 things. First, it increases acid production. Now, H. pylori can infect any part of the stomach, but most of the time it infects the antrum of the stomach, and when it does so, it causes inflammation in the antrum of the stomach, and that part of what occurs during that inflammation is we end up with a stimulation of the G cells. So we end up with gastrin, more gastrin, and suppression and actually destruction of the delta cells. So we end up with less somatostatin. And these two things work together to produce more acid. And also the inflammation stimulates sort of this vagal response. It stimulates the parasympathetic nervous system, which causes more acetylcholine to be produced, and that also produces more acid. So we have more gastrin is 1, less somatostatin is 2, and direct stimulation of the parasympathetic nervous system would be 3. And it all ends up with more acid. And then we have disruption of mucosal defense in the body of the stomach. And this is just due to inflammation and destruction of epithelial cells. And interestingly enough, there is some evidence that the H. pylori cells may actually feed on gastric surfactant. So we have a direct destruction of this gastric surfactant layer and a disruption of that mucosal barrier. So we have increased acid and we have disruption of the mucosal barrier. Now with NSAIDs, we actually have a similar process going on. Here, we'll go down here and we'll make a new part of my screen to talk about NSAIDs. And that, of course, stands for non-steroidal anti-inflammatory medications. So what happens with NSAIDs? Well, number one, NSAIDs, particularly the ones that have acetylsalicylic acid or other acids in them, are directly cytotoxic to the epithelial cells. So you have topical injury right off the bat. Now that's why we make all these enteric-coated NSAIDs. The idea is we're going to protect our stomachs from that initial insult from the cytotoxic aspect of the NSAIDs. Now what does that do? Well, if you kill off a few cells, then you disrupt the barrier, right? Because if you kill off a few of the cells, then the cells adjacent to them are going to be exposed to the acid on their lateral or basilar surfaces. Now another thing that will disrupt the barrier is inhibition of the COX-1 receptor. Now if you remember from pharmacology class, we have prostaglandins in our body, and prostaglandins are chemical signals that have receptors for COX-1, COX-2, and COX-3. And the theory is that COX-1 primarily influences organ systems, particularly the stomach and the GI tract, whereas COX-2 influences primarily somatic pain, and then COX-3 is actually involved with the central sensation of pain in the brain. So there was actually a theory back, actually the medications called COX-2 inhibitors were designed to only inhibit COX-2, whereas traditional NSAIDs were non-selective and inhibited COX-1 and COX-2. The theory was that if you made a selective COX-2 inhibitor, then you could avoid the gastric mucosal injury that is caused by COX-1. Unfortunately, the promise was very hopeful back in the 1990s when COX-2 inhibitors first came to the market. However, it turns out that they did not work as we theoretically thought they would, and there's a number of reasons for that. One is that there is a COX-2 mechanism of injury for COX-2 inhibition in the stomach as well, and I'll get to that in a minute. The other reason appears to be that the selective COX-1 and COX-2 inhibitors don't seem to be as selective as we had originally thought. But anyways, the COX-1 inhibitors, COX-1 inhibition causes decreased mucus secretion, which disrupts the barrier. It also causes decreased blood flow to the epithelial cells. Now, this is critical because this impacts the repair mechanism. It suppresses the epithelial repair mechanism. In fact, it can make it so that it is nearly non-functional because it can decrease blood flow to the stomach quite significantly. And then another effect that sort of relates is that COX-1 also impairs platelet function. And this doesn't cause injury to the stomach. However, if we do have injury to the stomach and we start to erode into small vessels, it just makes it more likely that the stomach is going to bleed. And then we have some COX-2 effects. If we inhibit COX-2, then we have significantly reduced angiogenesis, which again reduces the repair mechanism. And lastly, of course, NSAIDs suppress via both COX-1 and COX-2 suppress prostaglandin's ability to decrease acid production. So it ends up causing, NSAIDs end up causing increased acid production. However, this is not considered the central component of mucosal injury with NSAID use. By order of priority, I would say that disruption of the barrier mucosa is first. The loss of epithelial repair mechanisms is second, and increased acid production would be third. So if you did nothing but increased acid production, you would not end up with a gastric ulcer because the barrier mechanisms, the barrier protection and repair mechanisms would be enough to protect the gastric mucosa from the increased acid. So you really have to disrupt the barrier and disrupt the repair mechanisms in order for there to be injury. Now, peptic ulcer disease is also related to duodenal ulcer disease, and I'm not going to get into the details of that. Perhaps I'll come back later and make a separate video on duodenal ulcers. Duodenal ulcers are also caused by NSAIDs and H. pylori, and a lot of the same mechanisms are involved. Disruptions of the barrier. The duodenum also has significant repair mechanisms because it's exposed to acid and pepsinogen as well. But there's also, it involves some of the disruptions in the endocrine system that controls gastric hormones also causes decreased bicarb secretion by the pancreas, and that significantly contributes to duodenal ulcers. But again, duodenal ulcers and gastric ulcers are both most commonly caused by NSAID use and the infection with H. pylori. Okay, now that brings my discussion of peptic ulcer disease to a close. Please take a moment to provide some feedback with a thumbs up or a thumbs down, and if you have any questions, please feel free to ask them in the comments below, and I'll do what I can to answer them. I'm also going to provide a couple of links, one to subscribe to my channel if you haven't already done so, and another for quick and easy access to the gastrointestinal physiology and pathophysiology channel. Thank you very much.